let's begin today by doing some review in terms of drawing Lewis structures and applying those Lewis structures to doing things related to geometry and molecular shape. So we're going to start with selenium tetrachloride. To draw the correct Lewis structure, we know that we need 6 electrons for the selenium, 7 for each chlorine, for a grand total of 34 electrons. So if we draw our simplest Lewis structure, single bonds out to everybody, and we fill out all of the octets for the chlorines, where we're going to end up is each one of these is going to be 8, 2, 4, 6, 8. 8 times 4 is 32. So I'm 2 electrons short of where I need to be. And remember from chapter 4, if I am 2 electrons short, I need to turn that into another set of dots on the center atom. So selenium tetrachloride looks like that. So from this, we would look at this and go, okay, we need to figure out its steric number. Steric number, I have 4 atoms that it's bonded to, plus the 1 lone pair. So we're talking about a steric number of 5. Now for good practice, let's turn this into a 3D drawing using the dashes and wedges and our base model of what the trigonal bipyramidal looks like. So I'm going to have selenium here in the middle. I'm going to draw out my trigonal bipyramidal structure. And I know that the lone pair is going to go into this equatorial plane here in the middle, and that my chlorines are going to go everywhere else. And so here is my 3D shape for selenium tetrachloride. Now for context here, I'm going to draw using my molecular model here. The trigonal bipyramidal shape, which looks like this. And if I'm going to draw it out properly, I'm going to put the chlorines in position here, where they would go according to this structure. And then I'm going to pop off that extra bonding position in the equatorial plane, because that doesn't actually exist there. I'm going to use this ball here to represent that lone pair. And so what do I have left over here? Well, we can go to our chart. Our chart tells us that if I have trigonal bipyramidal shape with one lone pair of electrons, that we are talking about the seesaw molecular shape. Now, where does that seesaw come from? Well, now I can see it. Take this, turn it on its side, and you've got a seesaw. So in terms of answering the other components of this question, our domain geometry was trigonal bipyramidal. Our molecular shape is seesaw. And the bond angles here are going to be less than 120 and less than 90. Because this lone pair here is going to push down on all of these bonds. So these bonds, which are currently at 120, they're going to get squeezed together a little bit by the extra repulsion in this lone pair. These axial positions are going to get squeezed down a little bit by the extra repulsion in this lone pair. And so that's going to squeeze this angle from being a right angle to being 90 degrees. So I'm going to send this around and just kind of use it as a visual cue. Try to get your head around how those bond angles can be affected, how that can work as far as what we're trying to do is concerned. All right, let's take a look at another example. Let's look at the IF4+. So with IF4+, we've got 7 electrons for the iodine. We've got 7 for each fluorine, and there are 4 of them. But we are missing 1 electron because the positive charge takes an electron away. So again, 34 is our electron count. Now I'm going to give you a little hint into a way to make these a little bit easier to draw here. The very fact that we have the same electron count here and the same structure, basically, center atom bonded to 4 other things, tells us we're going to have the exact same molecular structure and the same molecular shape. The only thing that's really different is what atoms are there. So in drawing this, I can go through the same process. And come up with the fact that this is still 32 electrons at this stage, 8 around each fluorine, times 4, 32. So I'm going to need to put that extra set of dots on the iodine to get us up to 34, which means that my 3-dimensional structure would include iodine in this trigonal bipyramidal configuration. For the purposes of just being a little bit quicker here, we're going to leave off the lone pairs in our 3-dimensional structure since we already drew them in the Lewis structure there. We're just kind of looking at this from a standpoint of shape and angle. And so the net result here, once again, we have a steric number of 5. So we're talking about trigonal bipyramidal. With that lone pair in place, that means that we are looking at the seesaw configuration, and the bond angles there are less than 120 and less than 90 degrees. All right. Any questions thus far about either of these two examples? All right, let's move on to the triiodide ion, I3-1. For iodine, we had 7 valence electrons times 3 plus an additional electron for that -1 charge is going to give us 22. So if I draw iodine thusly and fill out all of the octets as I am supposed to do, all of those iodines now have an octet. Where are we in terms of electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Once again, we are 2 electrons short. And if we're 2 electrons short or 4 electrons short, however many short we are, those electrons go on the center atom. So for a lack of a better place, I'm just going to put them next to that iodine there, but really you can kind of put them anywhere. So once again, we need to evaluate steric number. Steric number here, we're looking at 2 atoms that it's bonded to, plus 1, 2, 3 sets of lone pairs. We're talking about a steric number of 5 again. So once again, we are talking about trigonal bipyramidal. Difference is this time, all of those lone pairs are all going to go in these equatorial positions in the middle of that ion. And the iodines are going to line up here in a row. So once again, if I'm looking at this from a molecule building kind of standpoint, if I start from a standpoint of my trigonal bipyramidal, but pulling off all 3 of these equatorial positions and replacing them with lone pairs of electrons, I should see that 2 things come out of this. First of all 3 sets of these lone pairs are all equidistant from each other. And being equidistant from each other, all of their repulsions are going to pull and push in opposite directions from each other. They're all going to negate each other, basically. So what does that do to this bond angle? Nothing. The bond angle here is still going to be 180 degrees because all of the pushing and pulling that these do is basically going to cancel themselves out. All that's left, because again, remember that these lone pairs don't take up any physical space that we can really see because electrons have virtually no mass compared to the atoms themselves. We're going to look at this molecule and say, it's linear. All the atoms are in a line. So from that standpoint, if we are looking at the geometry piece again, we're still talking about trigonal bipyramidal. But our molecular shape, because of all of those lone pairs, is going to be linear. And our bond angles, because all of those electron groups cancel each other out, is going to be 180 degrees. There's not going to be a shrinking of that bond angle in any kind of way because they all canceled each other out in the first place. Now, the reason I chose these three examples, I kind of warned you about this on Monday. We were going to overrepresent how often trigonal bipyramidal exists, mainly so that I can show you and help you get your head around that shape because it is the most different and kind of the hardest to put your head around. Now, I promise you with this last one, we're not going to have a trigonal bipyramidal. For one, we can't. Nitrogen and oxygen, neither of those are capable of breaking the octet rule, and you have to be able to break the octet rule to do steric number of 5. So if I'm looking at the nitrite ion, NO2 minus, what I see there is I have 5 for the nitrogen, 6 for each oxygen, and an extra electron from the charge. We're talking 18 total electrons. Now, if we draw this out from a Lewis structure standpoint, starting with the simplest structure, we would recognize that this Lewis structure, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, has too many electrons. And so if you recall, what we do when we have too many electrons is we have to take some away. And so we're going to need to make an extra bond here. Now, you will also recognize at this point in time that where we put that extra bond is completely arbitrary. What we have here is an example of resonance. Now, for this kind of practice, we don't need to concern ourselves with the resonance structures. That's a chapter 4 thing. We will ask you plenty about resonance with our chapter 4 stuff. Here, we just need to draw one of the structures, understanding that the other one does exist, but we're really trying to evaluate shape here. So if I look at this from a steric number standpoint, I have 2 bonded atoms, each of those oxygens, plus this extra lone pair. This is 3. We are talking about trigonal planar here. So to redraw this, Since all three of those positions are equivalent, where we put the lone pair does not matter. We can put it wherever we want. Usually out of convention, we put it up top. Now to evaluate the shape, we're starting with trigonal planar. This extra lone pair is going to affect that shape. And make it bent. And so, again, as an illustration here, here is my trigonal planar shape. If I remove one of these bonding groups and replace it with a lone pair, I can see that this is how I get that angular shape. So that's where the bend comes from. This is also going to push on these bond angles. So they are currently at 120. This is going to push on them a little bit more, bring them down below 120 degrees. All right, any questions on these structures? All right, so put a pin in this because we're going to come back to these exact structures again when we talk about the concept of polarity here in a minute. But before we get to that, I want to kind of see how you're doing overall in general. So I've got a question here for you. Not looking for all the bells and whistles here. I just want you to draw those two structures and evaluate them to figure out their molecular shape. So I'll give you a few minutes to do that. We'll come back and talk about it, and then we'll talk about polarity, and that'll probably end us for the day. All right, let's take a look. So if you're still working, go ahead and try to work some of this out on your own. If you're finished, let's see how we did. So if we start with the PSCl3, 5 for the phosphorus, 6 for the chlorine, 7 for each, 5 for the phosphorus, 6 for the sulfur, 7 for each chlorine. That gives us a grand total of 32 electrons. So phosphorus goes in the middle because it is the least electronegative. So if I put everything around it, I get this structure here. Now, from a formal charge standpoint, this is not the best structure because I have a positive on the phosphorus and a negative on the sulfur. To fix that formal charge, the best way to do it is to add a double bond there. Yes, it breaks the octet for the phosphorus, but it zeroes out the formal charge in the process. That's kind of one of those, it's better, but if you had it the other way, yes, it's technically wrong, but I wouldn't take off nearly as much as if you just had given me a structure that made no sense kind of thing. You know, we always want to be on the lookout for formal charge and trying to minimize it whenever possible. That conversation is kind of irrelevant to the idea of shape, because whether that's a single bond or a double bond, it doesn't make any difference in terms of its shape. For steric number, I'm dealing with 4 bonded groups and no lone pairs. So my steric number is 4. My domain shape is tetrahedral. And since there are no lone pairs, that is also the molecular shape. So tetrahedral is the correct answer here for the first one. For the iodine tetrafluoride ion, we've got 7 for the iodine, 7 for each fluorine, and an extra electron. It's going to give us 36. So if I'm drawing in my structure, and I do all the math here, 2, 4, 6, 8 times 4 fluorines is 32. So there are 4 electrons that need to go on the center atom. 1, 2, 3, 4. Well, now I'm dealing with a steric number of 4 bonding groups plus 2 lone pairs. Our group here is 6. So we are dealing with the octahedral domain geometry. But because 2 of those are lone pairs, that is going to slide us down, according to the chart, to square planar. And so if you're interested in how do I draw that 3-dimensionally, well, I've got iodine in the middle. And so my lone pairs need to be as far apart as possible. So they are going to occupy opposite positions. Most commonly, we use the axial positions for that, which would mean that the fluorines go here in the equatorial plane. This is where we get that square planar configuration. The fact that these 4 bonded groups are now making a square-shaped shape in this 2-dimensional plane going through the middle of the molecule. So the answer to this one here is square planar.